Hi everybody and welcome back once again, this time to lesson 13 of the Dead Earth game development series by myself, Gary Simmons, and brought to you by the Game Institute. Now in the last lesson we learned how to create an animation state machine to control which animation clips were playing at any given time. We implemented a very rough demonstration that saw us controlling a character with a controller, which fed the input axes into a 2D blend tree to select and blend the appropriate animations based on the severity of the input. We also saw how when using root motion, we get convincing character movement, which synchronizes up perfectly to the animations being played. And we demonstrated how the animator component can use this root motion to then automatically update the transform of the game object. Now this is all well and good when working with player-controlled characters, but when dealing with NPCs we have several complications to overcome. Now in earlier lessons we spent some time investigating Unity's navigation system and saw how we can use it to steer our NPCs in a way that has them navigating the level but without walking through any geometry, and also avoiding other dynamic objects such as other agents. We saw that this system too was in control of the game object's position, with the NavMesh agent component automatically updating the position and rotation of the transform each frame to keep the agent straight and true on its path. As both the animator component and the NavMesh agent components will both need to be present on our NPCs so that we can both animate and navigate them correctly, we appear to have a conflict. Both systems updating the transform of the same game object each frame with possibly very different data. One propelling the character based on the root motion of the animation clip currently being played, and the other based on the path that must be followed if the agent is to reach its target. Now there are several different solutions to handling this problem, and we're going to investigate some of them in this video. In my experience there is no perfect solution. And the solution I finally settled on for Dead Earth is a combination of the solutions that we're going to discuss in this video that worked well for my particular circumstance. Whichever system you choose, you will ultimately end up making some compromises unless you have a team of animators to develop the vast variety of turning variations for your locomotion blend tree, which I certainly don't have, and I doubt many of you will have either. So the solution I came up with addresses precisely that fact, where we're very limited with respect to animations. Now one solution, and the first solution that I'm going to investigate, will be to disable root motion altogether and let the NavMesh agent once again have sole control of the position and rotation of our game object as before. With root motion turned off, the animation playing will not be synchronized up in any way with the actual movement of the character, and therefore we're going to need to feed the NavMesh agent's desired velocity into the animator controller each frame so that we can try to select the correct blend of animations to play that most closely matches the speed and turn rate of the NavMesh agent. Now this will undoubtedly lead to foot sliding unless you have an enormous number of locomotion animations to cover all the turning, walking and running scenarios that the NavMesh agent may try to put our character through. I mean, even the simple example of our zombie walk animation will exhibit sliding because that walk animation did not have constant root motion speed. Now we will examine this technique anyway because in some scenarios it might be perfectly acceptable, such as when the nav agents do walk or run at a constant speed. And anyway, this is a technique that has been historically used in many games. The plus side of this technique is that the NavMesh agent will have total control over the transform of the character, so that our character will always be exactly where the NavMesh agent needs it to be. This means that the pathfinding and obstacle avoidance of our character is going to be at its most accurate. So let's start by implementing this technique. So the first thing I'm going to do is I'm going to select Jill in the hierarchy because she still has some of our scripts on that are left over from previous lessons and previous examples. You'll remember we have this controller script which we wrote at the end of the last lesson, and it was this script that read the input axes from the input controller and then passed them into our animator controller as the horizontal and vertical parameters. We don't want Jill to be controlled by the user input anymore, so I'm going to remove that script. We also have this speed controller script. This was a very early example that we did where we had a script that just allowed us to adjust this speed value in the inspector, and it would send that into the animator controller as a speed parameter. And we used that to demonstrate one-dimensional blend trees. This is no longer needed either. In fact, to be honest, you could actually delete both of those from your project, but I'll leave them there for now. So with Jill selected, we can see we now just have a transform component and an animator component. The animator component currently has apply root motion ticked. Now we don't want the root motion to control our character. So by unticking this, it means that when the animation is played, the animator will no longer use the root motion to update the transform. So that means no root motion for Jill. What we do need to do though is add a NavMesh agent component to this object and write a script that's going to talk to the NavMesh agent and tell it where to go. Now we already have a script from our earlier lessons that does pretty much most of this already. If you remember, we have this agent object in our scene which has a NavMesh agent component and that nav agent example script that we wrote. And if you remember, this script traverses a waypoint network, and each time it reaches a new waypoint, it changes to the next waypoint and it tells the NavMesh agent what its new destination is, sets the path and sets it on its way. So I don't really want to take this script and adjust it, because you may still want to play around with this script on some primitive objects. So what we'll do though, as this script has most of the functionality we already need, is I'm going to duplicate it in my project and call it something else, and then we'll make the amendments to that script so that it now fits our new purpose. So that script is contained in the navigation folder of our project inside the assets folder, and it's called nav agent example. So I'm going to select it with the left mouse button, then I'm going to click the left mouse button once whilst hovering the mouse over it, and that will allow me to rename it, and I'm going to call this nav agent no root motion. Now I'm going to open that up in MonoDevelop and change the name of the actual class, because of course the actual source code is still going to call this navAgent example. So what did I call it? I called it navAgent no root motion. navAgent no root motion. There you go. I suppose I should really update the comment as well, like so. Now the great thing about this script is we have this require component at the top of it, which tells Unity that whenever we add this script to any game object, because it relies on a NavMesh agent, Unity will automatically add a NavMesh agent to that object too. So if I go back to Unity and I select Jill in the hierarchy, and then I drag our NavAgent no root motion script onto it, you'll see that Unity will not only add this script, but it will automatically add the NavMesh agent component as well. I think I'm going to set the speed to a maximum of 5.6, which we know is roughly the maximum speed of the running animation in our blend tree. We discovered that in the last lesson. Everything else looks alright there. Now going back to our navAgent no root motion, you will recall that this script allows us to assign it one of our waypoint networks, which it's then going to use to fetch the waypoints and set the destinations for the NavMesh agent. So we'll drag over waypoint network 1. Remember, these were all created in our earlier lessons on the navigation system. Now, I'm not going to assign a jump curve because I'm actually going to get rid of that section of code. I'm just going to comment it out in the script because I don't really want to focus on jumping or anything like that yet, or off-mesh links. So with that script opened up, I'm going to comment out some of this stuff. So I think the first thing I'm going to comment out is in the update function where it says, if the NavMesh agent is on an off-mesh link, then start a coroutine that does that jump function that we wrote. And we're just going to ignore that for now. But everything else is exactly the same. So just to very quickly bring you up to speed, you can see that in the start function, we simply cache a reference to the NavMesh agent, and we then call the setNextDestination function. And all that function basically does is it tries to take whatever the current waypoint index is and uses it to fetch a waypoint from the waypoint network that we've assigned to this game object. And if the index is larger than there are waypoints in the waypoint network, then it will automatically wrap that around. So if we had 5 waypoints in our waypoint network, if we tried to get to waypoint 5, remember it's 0 base, so valid indices are 0 to 4, then it will wrap it back around to 0 again. So our agent will always just keep patrolling the same series of waypoints. And then you can see that in the update function, all we basically do is we say if basically the remaining distance to our current target has been met, then set a new destination. We also do that if the path, for whatever reason, has become invalid. Remember also, if the path becomes stale, then what we wish to do is just recalculate the same path again. So we call the set next destination function passing in false instead of true. When we pass in true, what the set next destination function will do is it will increment the current waypoint. So basically it means set a destination to the next waypoint in the list. Passing false basically says we want this function to set a path to the current waypoint we're heading towards. We just wish you to recalculate it again because it might have changed. Okay, so we know that just as we need to talk to the NavMesh agent component, this script is also going to need to talk to the animator component that is on Jill. So I'm going to create a private variable of type animator, and I'll call it animator, and I'll set it to null by default. And then, of course, what I would do in the start function is I will grab that reference from the game object by calling get component type animator, like so. Now in our start function at the moment, you can see that what we have is we have some commented out code where if we wish we can turn off the nav agent's ability to update the position and the rotation of our game object. I want to leave this commented out. In other words, in this particular script, I want the nav agent to update our transform and have total control over the position and rotation of our game object. So as it stands at the moment, we haven't done anything to send any parameters into the animator, but you'll see that our agent will correctly move Jill around the scene. And let me just choose the main camera. Yeah, everything's set up there. So if I press play now, there she is. Dun, dun, dun. She's running pretty fast too. So as you can see, this is just the nav agent dragging Jill around the level and doing absolutely nothing with the animator to tell it to try and just find some animations that at least fit the series of motions that Jill is going through. Oops, I need to turn off the agent, that cylinder, that's still doing its thing. Okay. So what we need to do now is we need to essentially figure out what the nav agent is about to do. In other words, how fast is it trying to go and how quickly is it about to turn. And then what we'll do is we'll feed this value in some shape or form into the animator and allow the animator to try and find the closest matching animation that it thinks would give a convincing result. So what I'm going to do for this example is I think I'm just going to leave the parameters as horizontal and vertical. And we saw that horizontal was in the minus 2.32 to positive 2.32 range, and vertical was in the kind of 0 to 5.66 range. So what we need to do is we need to get the current speed and the current turn rate, and we need to map them into these ranges. So what we're looking to do is in our update function, which if I just scroll down for a moment, we want to get some information from the NavMesh agent, which is going to tell us how much and in which direction it wants to turn, as well as how fast it is intending to go. So let's take a look at the NavMesh agent in the Unity documentation and take a look at the properties it exposes that might help us with the task at hand. Now you can see at the top of the variable list we have properties such as acceleration and angular speed. They are the properties that are exposed via the inspector and the ones that we set to define the limits of what the NavMesh agent is capable of doing. Therefore, they don't tell us what the NavMesh agent is actually doing. So one of the first things we might want to calculate is the turn angle so that we can determine which way we wish to turn and the severity of that turn. Now, one way we might do that is to use the waypoints of the path that the NavMesh agent is currently following. We saw when we wrote our editor script a few lessons ago that there is a path property of the NavMesh agent, and we saw that this is a variable of type NavMesh path. And one of the variables of this particular class is the corners array, which is just a vector-3 array containing all the world space points of the waypoints along the path. And we saw that the NavMesh agent essentially completes its path by heading towards each one of these corner points in order until it reaches the final corner point, which is its destination. In fact, there's an even quicker way to do this if what we're after is just the path point that we're heading towards, and that's because this is cached in another property called steering target. As you can see, this is a simple vector-3 that describes the waypoint along the path that the NavMesh agent is currently heading toward. So unless we're traversing an off-mesh link, this is always going to be a straight line between the NavMesh agent and the next point that it's heading towards. In the case of heading towards an off-mesh link, the steering target will be the entry point of the off-mesh link, and while the link is actually being traversed, it will point towards the exit point of the off-mesh link. Even so though, the steering target isn't what we want. You see, all of the points along the path were pre-calculated when we set the destination of the NavMesh agent, and that path was calculated only factoring in static geometry. Therefore, if we follow the steering target, we're not going to be aware when the NavMesh agent is trying to make any course corrections off of that path to avoid other dynamic objects such as other agents. Fortunately, the NavMesh agent exposes a property which is very useful. It's called the desired velocity. The desired velocity tells us the direction and speed that the agent wants to achieve. It's currently working up its velocity and its turn rate to reach that goal. Furthermore, this does factor in the contribution from the avoidance system. Therefore, the desired velocity tells us the direction that the agent is currently trying to rotate to achieve, and we can use this to calculate the severity of a turn that we can then feed into the animator to choose the correct animation to match. Of course, the desired velocity also tells us the speed that the agent is trying to achieve. So once again, we can use this to calculate our vertical parameter in our animator to select the correct blend of animations so that we get a walk and a run at the appropriate times. So given the desired velocity, how might we calculate our horizontal value? That's going to select the correct turning animation from our 2D blend tree given the severity of the turn. In other words, the angle through which we are trying to turn. The cross-product operation can really help us out here. It's a bit like a Swiss Army knife for 3D game developers. Now, if you've never heard of the cross-product or the dot product, then you're probably jumping the gun a little bit following along with the Dead Earth series at this point. I would suggest you take a step back and you go investigate our 3D mathematics material here at the Game Institute. And I also did some chapters on this early on in my old DirectX 9 course, so you might want to check out some of those early chapters from the archive section of our site. Simply put though, the cross product of input vectors A and B is a resulting vector that is normal to the plane containing both of the input vectors. Simply put then, the resulting vector is a vector that is perpendicular to those input vectors. Now that's pretty interesting information to know, and often that is why we will perform the cross product, but what's interesting to us in this particular case is the information that is encoded in the magnitude of the resulting vector. You see, the magnitude of the resulting vector is equal to the magnitude of input vector A multiplied by the magnitude of input vector B multiplied by sin theta, where theta is the angle between the two input vectors. Therefore, if we make sure that both of the vectors that we input into the cross product are unit length, that is, they have a magnitude of 1, the resulting vector will have a magnitude of precisely sin theta. Now I'm sure you're going to remember from your high school mathematics classes that once you've got sin theta, you could just input that into the a sin function and get back the angle in radians, which you could then convert into degrees. But actually, the parameters of our animator are not looking for degrees. We're just looking for some kind of scaling quantity that we can use to set the -232 to +232 range. Unlike the cosine of an angle, which is 1 at 0 degrees and 0 at 90 degrees, sin theta is 0 at 0 degrees and 1 at 90 degrees, so it becomes an excellent scaling mechanism for steering systems. As the angle gets wider, so too does the value between 0 and 1 that allows us to use more of our maximum turning ability. However, simply knowing sin theta between two vectors doesn't really help us. We don't really know whether we need to rotate to the right or whether we need to rotate to the left. It just so happens that in this example, if we imagine the input vector A was the forward vector of our character's transform, in other words, the direction the character is currently facing, and input vector B was the normalized version of the NavMesh agent's desired velocity, in other words, the direction we wish to be heading in, the resulting vector's y component will tell us whether we need to rotate to the right, where it will be positive, or the left, where it will be negative. So all we have to do then is perform the cross product between our transform's forward vector, our desired velocity vector but normalized, and we then test the sign of the y component of the resulting vector. If it's negative, it means we need to rotate to the left. If it's positive, we need to rotate to the right. In the case where it's negative, we simply negate the magnitude of that resulting vector. This will give us a value from the -1 to +1 range. Now remember, our animator controller has that horizontal parameter, and it expects to be given values in the -2.32 to +2.32 range. Hey, that's no problem. We just take that magnitude that we calculated, which remember is now in the -1 to +1 range, and simply scale it by 2.32. We can then simply pass it in as our horizontal parameter. So let's add that to our source code. So I'm in the update function here, and I'm going to put that just after the section of code where we fetch all of the various nav agent statuses. So the first thing I need to do is I need to perform the cross product between our transforms forward vector and our desired velocity vector, but normalized. That's a vector quantity that's going to get returned, so I'm going to say vector3 cross, short for cross product, equals, now Unity's vector3 class has a function to perform the cross product on two vectors, and it's called vector3.cross. So vector3.cross, like so. And then I pass in the two vectors. The first vector is simply going to be our transforms forward vector. Remember, that's a vector that describes the direction in which we're facing in world space. As the second parameter, I'm going to pass in the nav agent's desired velocity and use its dot normalized property, so Unity will give me back a unit length version of that vector. So now that we have our resulting vector, we need to get its magnitude. So what I'm going to do is I'm going to create a float. I'm going to call it horizontal, that matches our parameter, and this is how I'm going to assign it. I'm going to say if the resulting vector's y component is smaller than 0, in other words, if it's negative, then we wish this to be a negative rotation. So we assign to horizontal minus the resulting vector's magnitude. Otherwise, we simply assign it the straight magnitude. So this is in the -1 to +1 range. So what we'll do is we'll scale it into the -2.32 to +2.32 range. But what we'll do as well is we'll make sure it's clamped to those limits. So I'll say horizontal equals, and I'll use Unity's mathf clamp function. And as the first parameter, I send in the value I want to clamp, which is the value in our local variable horizontal, which is currently in the -1 to +1 range. And then I'm going to multiply that into the range that I want it, which is 2.32. And then I want to clamp the lower and upper limit. And the lower limit is -2.32, and the upper limit is +2.32, like so. So now we have this, we just need to pass this in to the horizontal parameter of our animator. Now, because this isn't going to be a production script, it's just a temporary script that I'm using to demonstrate some concepts, I'm not going to bother caching the hashes to all of the animator's parameters, so I'm just going to use the string version of the animator setFloat function. So I'm going to say animator setFloat. The parameter we wish to set is called horizontal. The value we wish to pass in is called horizontal. That's our local variable that's now in the -2.32 to +2.32 range. Now, I don't just want to pass this in without any damping. And as we discussed in the last lesson, damping allows us to smooth the values so that instead of just directly assigning our horizontal value to that parameter, we're essentially just assigning a fraction of it each time. So it's like we're, in a way, averaging all of the horizontal values over a period of time. So I'm just going to say 0.1 for the damping value and time.delta time. Now, the reason I wanted to damp this is because the nav agent's desired velocity can sometimes be quite spiky. It's not very constant. So if you're just taking it as is each frame, plugging it straight into the animator, you might see, especially at times where the nav mesh agent might reach one of the edge points on a path and it changes to the next edge point, you might see that desired velocity spike a little bit and judder a little bit from left to right. Of course, if we're just sending that into our animator, we're actually going to see our horizontal blender bar sliding from left to right as well in our blend tree, and that creates a very jittery sort of result as we see the character quickly alternating between a hard run left and a hard run right, for example. Okay, so let's calculate our vertical value as well. Well, the vertical value is pretty easy. That's just the magnitude of our desired velocity. Remember, the desired velocity is the speed and direction that our nav agent is intending to go. So the magnitude of the desired velocity is simply the speed. So I'm going to say animator.setFloat, and the parameter we wish to set is called vertical, and as the second parameter I'm going to pass in the magnitude of the nav agent's desired velocity. And I'll probably still just apply some damping to this so that the character doesn't abruptly change from a slow walk to a fast run. So there's a bit of ramp up time while the parameter reaches its value. So once again, as the final parameter, I send in time.delta time. When I save that off now and go back to Unity and check I haven't got any errors, which I probably have. No, I haven't. Okay, so we know that we've got a blend tree here, and we know that when we look at the vertical slider bar, it accepts a speed from 0 to 5.66. Anything larger than 5.66 is going to be clamped to 5.66, just because we have no animation that runs any faster than 5.66. So if the nav agent is going faster than that, we're going to get foot sliding and unrealistic animation. So it's up to us really when we select Jill to control the maximum speed that our nav agent is allowed to go. So I'm going to set this to 5.6, the maximum-ish. Then I'm going to press play and see what happens. Now let me just warn you before I press play. Remember, this is kind of an example of how we're not going to do it. I'm only showing it because we're going to borrow little bits from this technique in our final solution. But you're going to see at the moment where we really just have an idle and a locomotion state, that we have nothing in there to deal with turning on the spot and things like that. So when it gets to a point where the nav agent enters a room and then has to kind of back up and spin around and go back out of that room, we're going to see our character sliding around a lot. So just expect that, okay? Okay, here we go then. Disclaimer, well and truly out there. Whoa, yes, look at that. There you go, there's the sliding I was telling you about. Oop, nearly got skagged on the corner there, but you can see, although it's terrible when the nav agent reaches one of its waypoints and then has to kind of back out of the room, when it's just running around the level like this, it looks pretty convincing. And remember, there's no root motion here, we're just kind of guessing the speed really. And we're even guessing the angles, because although sin theta gives us back a kind of an angle really in the 0 to 90 degree range, both left and right, that doesn't really marry up in any way with our particular animations. We don't have an animation that runs us a hard 90 degrees to the right. So if we wanted to make that more severe, of course, then what we could simply do, we could just up the scalar. So I could say, I don't know, let me think. If we multiplied that by 4, for example, then, we're going to be getting hard turns from an animation perspective much more frequently, even when the angle isn't as severe. And that might even look better, who knows. It doesn't look terrible, does it? Apart from that bit. So there we go. And other ways that you can do it if you don't want to change the scalar in your code is you can literally just drag some of these animations into the center more so that they get triggered with a smaller horizontal value, so that you're basically triggering a harder turn with a lesser value. To show you the problems with this is you might look at this and think, well, all I have to do now is when the character enters a room and reaches its sort of next waypoint, we're seeing this horrible thing where it slides back out of the room. So what we would really want to do is have a turn on the spot there. But that's not going to be easy to implement with the animations that we have at our disposal. And the fact that the nav agent kind of navigates in a semi-unrealistic way with respect to, how it turns on the spot. Rather than stopping still and rotating, it kind of backs out and slides out while it's turning. So you would need some weird configuration of animations to actually make that look good without foot sliding. But let's have a go anyway and see if we can make this problem at least a little more bearable, even when not using root motion. So if you download the zip file that accompanies this lesson on the website, there will be a package file in there called testanimations2.unity package. I want you to import that by double clicking it, and there are actually some animations here that we might want to use for these tests. In particular, it has some turning on the spot animations, so let's import those. And they're Unity animations by Unity Technologies. So after the import is complete, if you go into your Unity Technologies folder, you'll see there is this default avatar turn on spot. You can see if you select it and look in the inspector, it actually contains several animation clips. Some are just partial turns. The only ones I'm really interested in are turn on spot right D and turn on spot left D, because these are the ones that do the kind of, they turn almost a full 180 degrees. So let's just check that these are looping. So I'm going to choose turn on spot right D first, and I'm going to click to loop time. Now if I press play, you'll notice that it's not really a glitch-free loop over. There's a little bit of a stutter once it gets to the end of the animation, and that's because this isn't a perfectly good looping animation. Now Unity has this little checkbox here called loop pose, which is really good for trying to fix up problems like this by blending the end and the beginning of the timeline together where they meet. So if I click loop pose, you'll notice now that we get a pretty glitch-free turnaround. So I'm going to click apply, and I'm also going to do the same for turn on spot left D. Once again, loop time enabled, loop pose enabled. Press apply, and let's just check that it turns round. Okay, so I'm going to drag in those two turn on the spot animations, turn on spot left, turn on spot right, and I'm going to create a new parameter in my animator, and it's going to be an integer. I'm borrowing from the technique we used, I think it was last lesson, where we had this turn on spot integer, and if it's set to -1 by our code, then it means we wish to transition to the turning left on spot animation, and if it's set to +1, then we wish to turn right. So I'm going to call this turn on spot, and then I'm going to make transitions between these various states, and these transitions are going to be powered mostly just by that turn on spot variable. So I'll make the transitions first. I'll leave the ones from idle. I mean, idle should have it too, but for now we'll see what it looks like just going from locomotion. So we're going to go from locomotion to turn on spot left, and I have to turn off exit time for that transition. And the condition is simply going to be if turn on spot equals -1. And we transition from turn on spot left back into locomotion, once again remembering to turn off the has exit time boolean. And the condition for this is simply going to be if turn on spot is greater than -1. I don't just want to say if it's equal to 0 then go back to locomotion, because it may be set to +1 if all of a sudden we realize we have to turn right. So in that case, if it was set to +1 and we were currently in turn left, it would transition to locomotion and then immediately transition to turn on spot right. So I'm going to do the same for those other two transitions. So we go into turn on spot right. If our turn on spot parameter equals -1, and we transition back into locomotion, remembering to turn off has exit time if turn on spot is less than 1. Now that's not really going to do anything at the moment because there is nothing in our code that is going to set turn on spot to 1 or -1. And what I'm trying to do here is I'm trying to detect when the nav agent has stopped, even if just fractionally, such as when it reaches a waypoint and it's about to change direction. And then what I'm going to do is I'm going to set this turn on spot value to either -1 or 1 respectively, and I'm also going to zero out the speed of the NavMesh agent until the desired velocity kind of goes up above a threshold. So basically we're going to stop the nav agent from moving for a little bit while this turn on spot animation is playing. So to see how that's going to work, I'm going to go back to my code and let's see what we have to do. So we're going to need to declare a local variable of type integer, and I'm going to call this turn on spot. And then at the bottom here where we set all of our animator parameters, I'll say animator set integer, and that's turn on spot is the parameter name that we wish to set, and that's simply going to be the value of our turn on spot local variable, which of course we haven't set yet. And I think what I'm also going to do, because I'm going to essentially reset the speed of the nav agent to 0, when the nav agent's moving again, I want to be able to set its sort of maximum speed back, because remember this is the speed that we set in the inspector. It's this value here. So when our agent stops, I'm going to set that to 0, and then I need to set it back to a value again. And I don't want to hard code 5.6. So what we'll do is we'll create a class variable called original speed, and then in our start function we'll cache what that was set to, and then when we set it to 0 and we need to set it back to its original value, we will have that value to hand. So I will go back up to my class variables, and I'll create a private integer, and I'll call this original, I'll call it original max speed, because that's really what that value is, isn't it? I'll set it to 0 because we're actually going to set that up in the start function. So I'm going to go down to the start function, and I'm going to say, assuming we have a valid reference to a nav agent, then original max speed equals navagent.speed. And then we have it there, so we can always set our navagent back to use that max speed in the future. Okay, so let's go back down to our update function now, and let's insert some code just prior to setting the parameters of the animator. Oh, by the way, guys, I just noticed I made an error. That original max speed should be a float, not an integer, because we're using it to store the navagent speed, which is not an int, it's a float. Sorry about that. Okay, so going back to our update function, what we need to do now is we need to implement the conditional code that is going to be executed when we should be in our turning on the spot state. So how can we detect when the turn on spot animation should be playing? Well, one of the things we can do is we can test the desired velocity, because if the speed of our agent ever drops to a very low value, then we know it probably means that it's at one of those waypoints where it needs to stop and turn around 180 degrees, or at least through a very wide angle. Because we know that when the nav agent is traversing our level normally, it doesn't slow down a lot when it takes shallow corners. So I think the first thing I will say is if navagent.desiredVelocity.magnitude, and we just need this to be smaller than some threshold. I don't really want to say 0, because the way that Unity's nav mesh agent works, when it comes to one of those stops, it may just be for like a fraction of a second that it's 0, or it may even be that it never actually reaches 0, but just to a very close number to 0. So I want to make sure I definitely catch that, and I can use quite a big value here, because I know that our walk speed in our blend tree is about 1.55, and our run speed is 5.66. So I know that if our desired velocity really ever drops below something like 1 or 0.5, then we know clearly our nav mesh agent is coming to an abrupt stop. So actually I think I'll just use 1 for now and see what that looks like. Okay. Now this conditional isn't finished here. Okay, we need to add another clause here, but I just want to map out what this piece of code is supposed to look like. So when we detect that the desired velocity of our nav agent has dropped to a low value, we want to actually stop the nav agent from moving, because we've seen on our previous nav mesh agent examples that what the nav mesh agent will actually do by default is it will literally stop for a split second, and then it will just like speed off in the opposite direction, perhaps spin 180 degrees on a dime, and it just doesn't look very realistic. So what we want to do is when we detect this is happening, we want to say to the nav mesh agent, stop moving at the moment, we've got some turning animation that we want to play, and we're going to let you know when it's okay to start moving again normally. So I could just set navagent.speed to 0, like so. However, if I set the nav agent speed to 0, this is going to cause some problems, because while I don't want the nav agent to move, I still want the desired velocity to correctly tell me the direction we're supposed to be moving in, because this is used to calculate our horizontal value. So we don't want to end up with a situation where we have a 0 vector. So what I'm going to do instead is I'm going to set the speed to a small value like 0.1, which will be pretty negligible. Now in the else clause, in other words, when our speed has got up past a certain threshold, which obviously isn't going to happen yet until we add a different conditional, we want to restore the nav agent speed back to that original value that we cached in our startup function, which is called original max speed. Okay, so obviously as it stands at the moment, if the speed ever drops to 0, the nav agent speed gets set to 0.1, and it will never ever get back up from 0.1, because this clause will never be executed again. And the reason for that is because once the nav agent's max speed is set to 0.1, the desired velocity's magnitude will obviously never be any greater than that, so it will always be less than 1. But don't worry, we'll deal with that in a moment. I just wanted to point that out. Okay, so the next thing we're going to do is we're going to calculate whether turn on spot should be negative or positive 1. And we need to do that by checking the sign of our horizontal parameter. If it's less than 0, we want it to be minus 1. If it's larger than 0, we want it to be positive 1. There's actually a really easy way we can do this using one of the functions from Unity's MathF library. It's called the sign function. If you pass it a positive value, it will always return a float of positive 1. And if you pass it a negative value, it will always return a float of negative 1. So I'm going to assign that to our turn on spot parameter. So turn on spot equals, and I'm going to use the MathF sign function and pass in the value of our horizontal parameter. Now because mathf.sign returns a float, we're going to need to cast that to an integer, because that's what our turn on spot variable type is. And of course, in the else clause, which we know will eventually be executed when it's time to start moving again, we definitely want to make sure when that's the case that turn on spot is 0 again, so that our animator doesn't stay in the turning on spot animation. So we'll set that back to 0. So at the moment, it's not going to work, okay? I'll warn you in advance, but you're going to see the turning behavior start to happen, but you're going to see, until we add an additional clause here, that once we step into this clause and set nav agent speed to 0.1, this clause is never going to be executed again to get the nav agents back up to its original speed. So we're going to be stuck in a perpetual turning animation with the nav agent moving us forward at just a max speed of 0.1. So let me go back to Unity and check I haven't got any errors. What I'm going to do as well is I'm going to just, I was tweaking with the camera and I set the speed down to 2, so I'm going to set that up to say 5. This is the speed at which the camera follows the character, because he's running quite a bit at the moment. I want to be able to keep him on the screen. And I'm going to look in the scene view because it's easier to see. I'm in the wrong room, bugger. Okay, let me run that again. So you'll see in this room here, when the character comes in, he will stop and then he will start to play his turning animation whilst rotating round, but then he'll never come out of that turning animation, and you can see that the nav agent is now moving us, but at that 0.1 speed. So what we need to do is find an additional condition that stops us stepping in to this, this code here, even if the desired velocity is less than 1. And that's simply going to be the angle between our forward vector and where we're supposed to be heading. You see, we only want to be turning on the spot up until the point when we're roughly facing in the right direction. As soon as the angle between where we're supposed to be facing and where we're currently facing is small enough, let's say less than 10 degrees, we also don't want to enter this code either. So what I'm going to say is I'm going to say we only step into this code if the desired speed is less than 1, and if the angle between the direction we're currently facing and the direction of our desired velocity is greater than some threshold. In other words, if it's quite a steep turn that we still have to make. And I'm going to use the vector3 angle function for this. We pass it 2 vectors, it returns the angle in degrees. So the first vector I'll send in is our transforms forward vector, the direction we're currently facing in world space. And the second parameter I'll send in is our nav agent's desired velocity. And then I'll say we only step in here if the angle between the two is greater than, I don't know, what should we say, 20 degrees maybe? 20 degrees. So if I save that off now, just to reiterate then, so when we go into the update function, when we find that our desired speed has dropped below 1 and the turn angle to get onto our desired vector is larger than 20, then we're going to set the nav agent speed to a very low value so that our desired velocity still maintains a proper directional vector. And we set our turn on spot parameter. So at this point, we're playing our turn on spot animation and our nav agent is not moving at all. Now, as we begin to rotate round, this angle here that is larger than 20 degrees finally falls below 20 degrees. In that way, we're facing pretty much in the direction we want to go, in which case the nav agent speed is restored, and we set the turn on spot parameter to 0 so that our animation state machine transitions back into the locomotion state. So I'm going to play that now. Now, it's not going to be brilliant, obviously, it's no root motion, but it should be as good as we can kind of get it at the moment. There you go, it's turning round, and then she's off again. It doesn't work too bad, does it? Especially if you look at it in the game view. Ouch. Okay, definitely detected a problem there. When the character went into the second room and turned on the spot, we didn't see the turn on spot animation playing. It was playing the walking animation whilst turning on the spot. I'm trying to figure out how on earth that is even possible. Okay, so the code must be getting executed correctly because the character stopped. So this must be something to do with the transitions. Oh, there you go. Okay, so I've got the wrong transition from locomotion to turn on right. As you can see, I say we go into the right turn if turn on spot equals -1. That should be 1. -1 is what we use in the transition into the turn on spot left. I think what I'll do also is I'll set the angle even tighter. So we have to get in like 10 degrees of where we wish to go before we start moving again. That's purely just so I can keep the thing on the spot a little bit longer in this video, so we can actually see it working properly. Okay, this should now work correctly. Fingers crossed. Want to look like an ass in public. Okay, stop, turn on spot animation, yeah, and then she's in 10 degrees threshold, so she starts off again. This was the one we had problems with before. Please, yeah, turn on spot animation. Off she goes again. So that's how we would do these sorts of things using purely solution 1. That's the solution where the NavMesh agent is controlling everything. And now, of course, you could get it looking a bit better than that, obviously, by tweaking some values and maybe speeding up some of those transitions into the turn states. But I just wanted to show you that it is kind of possible. But what I don't like about this is that it's all kind of messy. You know, we've got the code in our scripts that's kind of telling the animation state machine, you know, when it should be turning, and also having to tell the nav agent not to move until we're ready. And there's several different ways you could implement this, but I don't like this. The nice thing about the root motion approach is we don't have to bother syncing up any of this stuff. We just tell the animation state machine what the nav agent is trying to do, and then it will give us the information back and say, hey, this is what you're actually going to do based on the movement and rotation that is fetched from the current animation clip playing. So what we're going to do now is we're going to have a look at using that method. Okay, so I'm going to actually duplicate my script. I'm actually going to duplicate it this time. Unlike last time. And I'm going to call this nav agent, and I'm going to remove the no. Okay, so it's going to say nav agent no root motion is the one we did. This is nav agent root motion. Now, these scripts, none of them we're keeping, okay guys? I mean, these are just to show some concepts off. I'm just going to adjust the comments here. So we've now investigated option 1, where the NavMesh agent has total authority over the transform of the game object. And while at times it looked fine, there were also times when it looked like, let's face it, 7 types of crap. So let's now investigate option 2, which is to enable the root motion in the animator, and then use that root motion data to set the velocity of the NavMesh agent each frame. In such a scenario, we would instruct the NavMesh agent to no longer update the rotation of our game object, and would instead set the rotation to that dictated by the root rotation data in the animation clip. The NavMesh agent would still update the position of the object, but based on a velocity that we give it from the root motion in the currently playing animation clip. Each frame, we will examine the desired velocity of the NavMesh agent, which we know tells us the direction and speed that the nav agent would like to achieve. We use this desired velocity vector to calculate a speed and a turn angle that we can then use as parameters for our animation state machine. What we are saying to the animator is essentially, this is the speed, the direction, and the rotation that the NavMesh agent wants us to perform. Please find the animation in your blend tree that most closely matches this. The animation state machine then calculates the root motion and rotation, but instead of updating the game object automatically, passes this data to us via a function of one of our behaviors. The returned rotation and velocity, however, might not be exactly what the agent wanted. It will only be as close as the blend tree can get with the animations it has stored in it. We then override the current velocity of the NavMesh agent and set it to the actual velocity that was generated by the root motion. And we directly set the rotation of the game object ourselves to the root rotation fetched from the animation clip also. So in short, the process goes something like this. The NavMesh agent says something like, I want to turn 85 degrees and travel at 6 kilometers per hour. We then override this velocity to say, you can actually only turn 60 degrees and move at 4 miles per hour. The speed of the NavMesh agent is taken directly from the root motion, and the root rotation is used to set the transform of the game object directly. Now the plus side of this is that we will once again have convincing root motion movement in our scene, just like we did in our demo at the end of the last lesson, where we had our Jill character being controlled by an input controller. The downside is that because we are not always giving the NavMesh agent what it wants, and indeed what it expects to get, but only the best the animator can give it, the navigation will be much less accurate unless we once again have a massive variety of turning animations to fit all potential scenarios. And unfortunately, the NavMesh agent does some pretty unrealistic movements at times, so it's unlikely we will have such a set of animations at our disposal. Therefore, it is more likely that our character at times may not have the desired turn angle the NavMesh agent wants, and may occasionally knock into walls, doors, or overshoot the mark. And I saw something very similar when I was first developing Dead Earth using just the root motion approach. There was this situation where I had a zombie, in fact it was Jill, chasing me, and to try and get out of her line of sight, I ran into a house. As I ran into a house, there was a staircase immediately to the left, so it was like a 90-degree turn. I ran up those stairs to hide from Jill. She followed me into the house, but she didn't have the turning angles from the available animations in her blend tree to go through that door and then make the sharp left that I needed her to make. And she overshot the entrance to the stairs and then got herself in a bit of mess, actually, just trying to get lined up again so she could get up the steps. So we're going to address all of these problems, and you're going to see how I combine both of the solutions we've covered so far to come up with something that works pretty well, and I'm quite happy with. Okay, so I think the first thing I'm going to do is that animation controller that we've just created for the no root motion scenario. We currently put that in the My Test controller, which we've been using pretty much for everything and just adapting it. So just in case you want to keep that one and play around with it, I'm going to rename that and call this Nav Agent Authority. And then I'm going to duplicate it, okay, so that we leave that one intact if you want to play around with it and assign it to Jill whilst doing your tests. So let me duplicate that, and I'll call this one Root Motion Authority. Root Motion Authority, okay? And then I'm going to assign that one to Jill now, because this is the one we're going to be working on next. So if I open that up, I'm going to get rid of pretty much everything from this animator, like so. Just trying to remember what idle clip we used. Actually, I'm even going to get rid of the idle clip because that package that we imported a few moments ago contains a more generic idle clip that, to be honest, probably suits the walking and running animations and stuff that we're using. So let's put the idle clip in first. So if you go into your Unity Technologies folder inside your animations folder, you'll see there is a default avatar neutral animation. Looks like so. Just sways from side to side. And I just want to make sure that the loop time and loop pose are set, which they are. So I'm going to drag that into my state machine, and then I'm going to make another blend tree. So I do create state from new blend tree, and I'll just call this blend tree locomotion again, like so. And then I'm going to hook up some transitions to and from idle and locomotion. And then what I'm going to do is I'm going to delete all of these parameters. Like so. And then what I'm going to do is I'm going to create my new parameters. They're going to be floats. The first one's going to be called angle. This one's actually going to take an angle in degrees that we wish to turn because it's a little less cryptic, I think. And the next float is going to be speed, like so. And then what I'm going to do is I'm going to click into the locomotion blend tree, and I'm going to assign 3 motion fields. I'm not going to do a 2D blend tree this time. I'm just going to do a one-dimensional blend tree, and I'm just going to basically use a tight walk left, a tight walk right, and a walk forward just to demonstrate the process. So they are in my Unity Technologies folder. So I think I will go to the walk short, which is the very tight turn. So I'll put left in there, I'll put right in there, and then we want just the walk forward, don't we? Which is walk forward there, that's the one, neutral face forward, like so. And I'll drop that one in the middle. Then what I'm going to do is I'm going to click unautomate thresholds, and because this is a one-dimensional blend tree, we essentially have a fixed speed for our character. So, and we can try this with run animations and everything later on, but for now I'm just using walking animation. So the only parameter that this blend tree needs is the turn angle. So I'm going to base that on angular speed degrees. And as you can see, it's automatically calculated what the turn is, sort of intrinsic to each of those animations in the root motion. So let's just see if that works right. So we've got a very tight turning angle left and a very tight turning angle right. And at a walk speed, that should pretty much get us everywhere we want to go. And of course, we also need to set the parameter for this 1D blend tree. It's currently set to horizontal, which would give us an error because that parameter doesn't even exist anymore. That now has to be set to angle, which is our turn angle. Just check that works. Dun, 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 dun. Yes. So now we need to think about the transitions and how we're going to use those. So I think the transition from idle to locomotion, we'll just do something nice and simple. And we'll say if speed is, essentially if speed's greater than 0, but I'll put some sort of threshold in there. So I'll say 0.5. Then the animation from locomotion back to idle, once again remembering to untick the has exit time, is simply going to be if speed is less than 0.5. In other words, if we've come to a stop. So at the moment it's quite simple. Speed is driving our transitions to and from the locomotion state, and angle is driving the locomotion blend tree to choose the correct walking animation based on our turn rate. So now we need to do a few other things. So if I select Jill, what we wish to do now is we wish to re-enable the apply root motion settings. What I also need to do, because I'm seeing a little error along the bottom of the screen here, is I still have that second layer called the attack layer, which is trying to access my attack parameter, which I've deleted. So I'm just going to delete that entire layer. So we're just left with the base layer. Keep things nice and simple. And I clear that error from the console window. So if we go back to our code, there's a few things we're going to need to add and some things we're going to need to get rid of. We no longer need that original max speed that we were using to set the speed of the NavMesh agent. It's not going to be up to the NavMesh agent anymore how fast we go, so I'm going to delete those. And what I do need to do in the start function is remember this code that we have commented out that basically told the NavMesh agent not to update the position and rotation of the game object. Now we still want the nav agent to update the position, but we no longer wish it to update the rotation. Okay, so as you can see, I've left update position commented out. That still needs to be set to true, but I have set update rotation on the nav agent to false, so it will no longer try to update the rotation of our game object. So, and finally, in the update function, we kind of really want to get rid of all of this stuff here. That's all the stuff we added in the first half of the lesson that deals with the horizontal and vertical parameters. So bye-bye. All that hard work gone. And we can also get rid of that turn on the spot variable too. Let me just check I've not got any errors. Okay, so I'm going to show you now something that's really cool about MonoBehavior and the animation system. If I implement a function with a void return type and call it onAnimatorMove, look what it says if I now go back to Unity and select Jill from the hierarchy view. Oh, of course, hang on. First of all, we haven't assigned our new script to Jill, so we need to get rid of the old script, or just turn it off, which was the one called navagent no root motion, and we need to go down to the navigation example folder and drag over the navagent root motion script like so. Now, you may not have noticed this, but when I dragged that script over, something quite magical happened in the animator component. Where we had that apply root motion tick box and we had it ticked, it's now been replaced by a line that says handled by script. That's right, folks. That onAnimatorMove function is where we're going to get access to the root motion that would have been applied to our game object by the animation system. But instead of the animator now automatically doing that, it's going to give it to us in this function, and then we can choose what to do with it. Now that could be something as simple as mimicking the steps that the animator does by simply applying the root position and the root rotation to the transform of our game object, or we can do something altogether a little bit more cunning, which is what we're going to do. Now, one of the really useful things about the onAnimatorMove function is where Unity calls it in the flow of execution. It happens just prior to the late update pass. So at this point, all of our objects have had their update functions called. They've all had their properties set according to our scripts, and also the root motion and root rotation has been calculated. But the internal representations of our game objects inside the scene graph that is maintained by Unity has not yet been updated. So it makes it an excellent place for us to just pop in at the last minute and override some values before Unity uses those values to truly update the object in the scene. And we're going to use that to calculate a velocity that will then be used to set the final velocity of our NavMesh agent. So in our update function, what we're going to do is we're going to use the desired velocity to calculate the speed that the nav agent would like to go and the angle that the nav agent would like to turn, and then we're going to feed that into our animator via the angle and speed parameters. Now when the onAnimatorMove function is called, the nav agent hasn't been updated yet, so we still have a chance to set the final velocity that it's going to use to update itself, and we're going to take that information from the root motion, which will now be available to us in the onAnimatorMove function. So one of the things you're probably thinking is, how do we get this information? This function takes no parameters. Well, it doesn't need to, because if we look at the Unity documentation for the animator component, you will see that it has some properties that contain this information at the time the onAnimatorMove function is called. If I scroll down to near the bottom of the variable list, you will see that there is root position and root rotation. Now these properties essentially contain the position and the rotation that the animator would have set the transform of our game object to use were it applying the root motion itself. So this isn't exactly what we want from a positional perspective, because we need to calculate a velocity for our nav agent. The root rotation though is exactly what we want. It is what the rotation of our game object should be in the world according to the root motion that just played out. So if we take that root rotation and just assign it directly to the rotation of our transform, we've essentially done exactly what the animator would have done had we not implemented the onAnimatorMove function, and our object truly will have its rotation driven by the root motion, which is exactly what we want. So we're going to say transform.rotation equals animator.rootRotation, like so. Rotation taken care of. It's being completely driven by our animation. However, we don't want to do this for our position, because if we were just to override the position of our transform using the animator's root position, we're just going to be completely dominated by whatever the animation clip tells us should happen to our game object. So that's why at the start function we left it such that the NavMesh agent was still in control of updating our position. What we want to do is say, still do your thing, but we're going to tell you the velocity at which you should be moving yourself and our game object. So do we have a root motion velocity inside the animator components variable list? Well, we don't, but what we have instead is we have delta position and delta rotation. So delta position tells us just how much we've moved since the last frame. And delta rotation, which we're not going to need here because we're just overriding the rotation, tells us how much we've rotated since the last update. But the delta position information is all we need to calculate the velocity that would have been applied to our game object by the animator were it automatically updating the transform of our game object. What we're going to do, however, is calculate the velocity that our object would have been traveling at had root motion been applied automatically, and then we're going to give this to the NavMesh agent and say we want you to mirror this velocity, so that when the nav agent updates itself and our game object, our object is going to move at exactly the same velocity that it would have moved had root motion been automatically applied by the animation system. So how do we get velocity from delta position? Well, actually, it's quite funny, because normally when you're writing 3D graphics engines, it's the velocity that you know, and you integrate velocity over time to get delta position. Remember, velocity is a direction and magnitude that's measured in meters per second. So if we multiply that by time.delta time, what we're doing is we're finding out how much we've moved for just that time slice that we're currently processing. So in this particular situation, we've got it the other way around, right? We've got delta position tells us how much we've moved in just this particular time slice. So if we divide by time.delta time, we get that back into a per second value. In other words, we get back velocity. So all we have to do in our code is say navagent.velocity equals animator.delta position divided by time.delta time. Now once again, because this is not production code, we would normally do some sort of check on time.delta time to check that it wasn't 0, so we don't get a divide by 0 or anything like that, which could happen if you've paused the game or you've frozen time or things like that, but we're not going to be doing anything like that at this point. So that's our onAnimatorMove function complete. Now there's no point running this at the moment because we haven't put anything in our update function to drive what's going to happen in the onAnimatorMove function. We need to first, in the update function, send our animator our speed and angle that we would like to go based on what our nav agent tells us. And then we come into the onAnimatorMove function and we tell the nav agent, actually, this is the direction and speed that you're going to move. So let's now go back up into our update function and start putting some code in there that's going to allow us to calculate the turn angle and the speed that we're going to send into our animator. So I'm going to start by calculating the angle, and for this I'm going to use a little bit of high school trigonometry. Oh joy, I hear you all scream. Seriously though, it's pretty simple stuff. I'm going to start by taking the desired velocity vector of our NavMesh agent, and I'm going to inverse transform it into the local space of our game object. So if we imagine what this looks like on the XZ plane, the desired velocity vector in local space forms the hypotenuse of a right-angled triangle where our character is assumed to be staring down the adjacent leg, which is described by the z component of that vector, and of course the opposite leg of that triangle is described by the x component of the vector. Now we also know from our high school trigonometry classes that if we know the length of the opposite leg and we know the length of the adjacent leg, then opposite over adjacent equals tan theta, where tan theta is the angle between the adjacent leg, in other words the direction our character is currently facing, and the hypotenuse, which is our desired velocity vector. It's exactly the angle that we're looking for. Now once we have tan theta, what we could do is we could send that into the arctangent function to get back the angle in radians, which we could then convert into degrees by multiplying it by 360 over 2 pi. However, Unity has a math function that's going to make that a little bit of a shortcut, and it's called the atan2 function. We simply pass it in as the first parameter, the length of the opposite leg, which is the x component of the local space desired velocity vector, and we pass in as the second parameter the adjacent length of the triangle, which is in this particular case the z component of our desired velocity vector. And then that function will automatically behind the scenes perform the opposite over adjacent calculation and do the arctangent function for us, and it will give us back the angle in radians, which we can then just convert into degrees, and voila, we have our angle. So let's see what that looks like in code. So like I said, the first thing I'm going to do is I'm going to convert the desired velocity vector of the NavMesh agent into our local space. So this is going to be a vector 3, so I'm going to call this local desired, I'll just call it the full thing, what the hell, local desired velocity equals, and we can use a method of the transform class for this. It's called inverse transform vector, like so, and it just takes a vector, so we're going to pass in the nav agent's desired velocity vector. Now there should probably be some checks here just to make sure that desired velocity doesn't have a length of 0 or anything like that, but like I said, this isn't production code, so it doesn't really matter at the moment, not going to cause a problem. And we're also going to apply that sort of smoothing anyway, so if we get any spikes in our desired velocity, they're going to be pretty much diluted by the damping. So local desired velocity now contains the direction that we wish to move, but specified relative to us, relative to our local forward vector. So like I said just now, the x and z components of this vector form the opposite and adjacent legs of a right angled triangle, so we can send that straight into the atan2 function. So I'm going to say float angle equals mathf atan2. As you can see, that takes two parameters. The first is the x component of our local desired velocity, the opposite leg, local desired velocity.x, and as a second parameter we pass in the z component of that same vector, local desired velocity.z. Now that's going to give us back the angle between our forward vector and our desired velocity vector, but it's going to be specified in radians. We want that in degrees because that's how we've set up our blend tree. So in order to do that, we just multiply the amount by mathf dot rad to deg. There it is. That's a constant that's defined in the math class. It's basically just the result of 360 over 2 pi, which is the scalar you need to multiply radians by to get them into degrees. So this gives us back the angle in degrees, and we know if it's minus 10, then we need to turn 10 degrees to the left. If it's positive 10, we need to turn 10 degrees to the right. So I could just send this into the animator and do some damping, but I think to be safe, I'm going to perform the smoothing myself using Unity's mathf.moveTowardsAngle function. This is a function that moves a variable towards the value of another variable, but treats it as an angle, so that if there are any issues rolling over the 360/0 degree mark, it automatically treats it like an angle and wraps it round. So, if we were at 355 degrees and it wrapped past the 360 degree mark, it would wrap back round to 0, and vice versa in the other direction. So in order to do that and perform the smoothing myself, I'm going to need to go back up and create a private variable in this class. It's just a float, and I'm going to call it smooth angle, and I'll set this to 0 by default. And then back in our update function, we will say smooth angle equals, I'm going to use that mathf move towards angle function. There it is. So the first parameter is the value that we're moving from. So that's the current value of our smooth angle variable. And we wish to move that towards the angle variable that we just calculated above. And then as the third parameter, we specify what they call max delta, which is just the maximum step that we're allowed to take from smooth angle towards angle. And we want this to be scaled by time.delta time as well, so it's frame rate consistent. So I'll say 80.f times time.delta time. And I think if I understand that correctly, that's basically going to mean that we're never going to be able to move more than 80 degrees in a single second. So that seems like a pretty nice smoothing amount. It's fast enough to be reactive. It's slow enough that if we do get any spikes in the desired velocity, they're probably not going to show up. So now we just need to pass that into our animator using the setFloat function. And once again, I'm just going to use the string versions of these functions because this isn't production code. And I did call it angle, didn't I? Let me call up the animator. Yes, angle and speed, both with capital letters at their beginnings. So angle, and then I'm just going to send in our smooth angle value. There you go. Okay, so what we're going to send in for speed? Well, that's pretty simple. I'll just use the magnitude of the desired velocity vector, which we've used many times before. So I'll create a local variable for this, just to keep the code nice and readable. So I'll say speed equals, and I could use either the local desired velocity vector here or the NavMesh agent's desired velocity vector. They should both have the same magnitude. They're just in different frames of reference. So I'll just use my local desired velocity vector dot magnitude, like so. And then underneath here, I will say animator dot setFloat. The name of the parameter was speed. I'm going to send in our speed value, and I'm just going to assign damping to this like I've done in all of my other demos, just so we slowly ramp up the animation, so we don't get any very sharp transitions inside our blend tree from like a hard left to an upright or an upright to a hard right. So 0.1 I think is what I used, and of course when we're using damping we also have to send in time.delta time, like so. Okay, I've done an underscore by speed. It's a local variable, it shouldn't have an underscore there. Let me just get rid of that. And then we do have a little bit of scene setup to do before we press play. Yeah, so just remember that we're now using this navagent root motion script, not the navagent no root motion script. In fact, I'm going to delete that older script from the game object altogether. But the newer script has not yet been assigned a waypoint network, so I'll just assign it waypoint network 1. Now the other thing we want to do is we want to give this a little bit of stopping distance. The stopping distance property is just a way of us saying to the nav agent, if you get within a certain threshold of your target waypoint, then just consider this as having reached it. Now this wasn't really an issue before when the NavMesh agent was controlling it, because it was using auto braking and it would always exactly hit that distance of 0 from its target waypoint. However, because we're using root motion now and the nav agent really doesn't have control over its own velocity, there's a real chance that, let's just say for example the NavMesh agent was 1 meter away from its path endpoint, and then we got told from the root motion that we had to move it 2 meters, it would overshoot the mark and then it would still be a meter away from its target point but on the other side. And what you tend to see when this happens, and the reason I'm saying this because you might see this quite often when you're experimenting, is you might see a nav agent going crazy, just looping round and round and round a given waypoint, not being able to actually reach it because it doesn't have the turn angle. So we'll just say if you get within 1 meter of it at a walk speed, that should be enough. Oh, I'm also going to set the speed of the camera down to something like 2. So it moves a little bit more slowly, because we had it set to 5 as its interpolation speed. Our character is walking now, not running, so it'll look a little nicer and we'll be able to see more of the character. Okay, fingers crossed, root motion. Here we go. So there you go. We've got no turn on the spot animations at the moment, guys. Just remember that. So it's going to try and do everything just with the turning animation that it has. So you can see at times it kind of may snag a wall or something because it's trying to do a complete kind of 360 turn. Looks pretty good though, doesn't it? I don't think it's going to make it out. Oh, there you go. Slightly caught the wall. That's because it didn't really have the turn angle. Under normal circumstances, it would have done a stand on the spot and turn 180 degrees type of maneuver there. Don't worry, we'll add that in a minute. I just want to show you something else first. And there you go. So now the root motion is controlled. The animations look great, but we're having a problem getting turn angle. Now, one of the things that we can easily do to fix that is, although we're sending in the angle to our animator, it doesn't really mean that much in the real world. We want to be able to tweak that. So if I select the blend tree in Geo's animator, you'll notice that at the moment we're only fully executing the tight walk left and the tight walk right when that threshold reaches over 100 degrees. Now really, that's not a really steep turn, is it, if you look at it in the animation? So I think we can bring those in a little bit so that they're triggered earlier, and that will give our character much better maneuverability. So instead of triggering these animations fully at minus 101 degrees and at positive 101 degrees, which quite frankly we probably very rarely get to, I'm going to set them to minus 40 degrees and positive 40 degrees, like so. And really that walking animation should probably be set to 0, because we want this to be triggered when there's no rotation at all. So of course what we've done now is we've essentially brought those left and right walking animations closer to the center line of the graph, so that now at 40 degrees we're performing our most severe turn that we have available. And obviously at 20 degrees, whereas before we were only really executing the walk animation with 1/5 of our most severe turning animation blended in, at a 20 degree turn now it's actually a 50-50 blend between our walk animation and our tightest turn animation. So it just means that our character is going to be turning more aggressively, and this will give it more maneuverability. So let's see what that looks like. Don't worry if this is a little bit jerky in the video, guys. It's probably just the screen capture software. You can see it missed that wall there. It's doing tighter turns in there now, and it'll probably get out of the room even without a turn on spot with that maneuverability. See what I mean? So you can always adjust the blend tree to get the maneuverability that you want. Yeah, that looks pretty good to me. Oh, we're getting somewhere. We are getting somewhere indeed. Okay, so what we probably want to do now is add those turn on spot animations so that we have a kind of state machine that handles all scenarios. So I'm going to go down into my animations folder and my Unity Technologies folder, because that's where our turn on spot animations are contained. Now, in all the examples up until now, I've been using turn on spot left D and turn on spot right D, which gives us this very quick sort of 180 degree about turn. Now I don't want to use this one this time. I want to use the C variations or any of the other ones, but I want to use something a little more shallow, and the C versions of the rotations rotate us about 90 degrees, a little bit more perhaps. And the reason I don't want to use the turn on spot right D and the turn on spot left D animations is because our angle parameter and our speed parameters are being smoothed. So they take quite a while to register when even a big angle change has happened. And we've also got a situation where we have transitions that also take a certain amount of time. So we might find ourselves in a situation where I'm going to say 80 degrees is my turning threshold. So when the angle between our desired velocity and our current forward vector is greater than 80 degrees, either to the left or to the right, we're going to drop back into idle from our locomotion state, and from there branch out into one of the turn on spot animations. So let's just say that I am currently rotated 81 degrees to the left of where I want to be. So in that particular scenario, we would branch into the turn on spot right animation. Now this animation is going to turn me very quickly to the right, and our angle parameter is being smoothed, so it could take me a while to really register when I'm facing the direction I want to go in. Add on to that the fact that there's going to be a transition out of the turn on spot animation into the idle animation where we're still going to be turning a little bit. And what you can find, and I know this because I got it from testing, is that it was turning so quickly that, let's say I was 81 degrees to the left, by the time I came out of it, I was more than 80 degrees rotated to the right. And then that would trigger a turning left on the spot rotation. Same thing would happen again, which would then trigger a turn on right spot animation, and I would find myself in a perpetual spin. So I just want to use something that's a little bit more of a shallow turn that's going to turn in more baby steps. So we haven't used the turn on spot right C and the turn on spot left C, so we better just select the turn on spot animation, select them in the animation list in the import inspector, and just make sure that we've got them set to loop, which we haven't. Click apply, and then do the same for turn on spot left C. Click apply, and then I'm going to drag them into the animator. So like I said, what I'm going to do is I'm going to have a threshold of 80 degrees. So when we're in our locomotion blend state and we determine that we need to turn more than 80 degrees, which is either minus 80 or positive 80, depending on whether it's a left or right rotation, we're going to drop back into idle. Now at the moment we transition from locomotion to idle when speed is less than 0.5, and the same in reverse. I'm going to just turn that down to 0.1, okay? 0.5. Still kind of half a meter, it's quite fast. So that should stop us dropping back into the idle animation too short of the mark. Because remember, it doesn't matter what the nav mesh agent wants to do. Once we drop back into the idle animation, that nav agent ain't moving anymore. Not until we get back into the locomotion state, because our animation state now controls the velocity of the nav mesh agent. So what I'm going to do is I'm going to add 2 more transitions from locomotion to idle. And the first of these transitions is going to say, oh by the way, I don't want to keep saying it every time, but for all of these transitions I'm about to create, I'm going to turn off has exit time, okay? Okay, so we're going to go back from locomotion into idle if the angle is greater than 80 degrees. And in the other transition I added, we drop back into locomotion if the angle is less than minus 80 degrees. Same thing, but to the left. And likewise, we're only going to go from idle and resume walking if our speed is greater than 0.1 and our angle is not less than minus 80 or greater than positive 80. So I don't need to add additional transitions here, but I do want to add additional conditions to this transition. So I only want to transition back into locomotion from idle if speed is greater than 0.1, if the angle is greater than minus 80, and if the angle is less than positive 80. So now I'm going to make some connections into these turn on spot animations and transitions back into idle. And of course, if we're in idle, the transition into left is simply going to be kind of what we've seen so far. If the angle is less than minus 80, and you've probably guessed what the transition is going to be into the turn right animation, it's going to be if angle is greater than 80. So we now know that 80 is the threshold at which we turn on the spot. But now we need to decide what the threshold is going to be for us to come out of turning on the spot. You see, we don't need to get exactly aligned with the direction that we're facing before we start walking forward again. Remember, our locomotion blend tree still has plenty of turning ability as well to sort of make it the rest of the way. So what I'm going to say is, if we're larger than 80 degrees misaligned and we start to rotate, once we get within a 40 degree threshold either side, I'm going to come out of the turn on spot and we can resume the locomotion and just allow the turning animations in the locomotion blend tree to take us the rest of the way towards our desired direction. So we're going to come out of turn on spot right if the angle is less than 40 degrees, and we're going to come out of turn on spot left if the angle is greater than minus 40 degrees. Okay, so I think that's going to work. There are going to be some problems with this, I'm going to warn you, but we're going to solve those in a moment. But what you're going to see, I believe, is when our character walks into that first room, you're going to see when it reaches its waypoint, it's not going to stop in time. It's going to walk a little too far and start to turn to the left. There you go, and then it stops and turns. And this is really just a problem of using the desired velocity's magnitude to set our speed, because we really need to rely on the speed to bring us to a stop here, not the actual angle, because our angle has quite a lot of smoothing on it. So when we've reached our sort of waypoint, it's going to take a little while for the angle to kind of catch up with the desired velocity direction. So we're really relying on the speed there to drop us down to 0. But that doesn't actually happen, because as speed we're using the magnitude of the nav agent's desired velocity. And as soon as we hit that waypoint, the desired velocity flips 180 degrees, but it's still the same length. In fact, it's pretty much always the length of the speed that we set in the inspector, which is currently 5.6. Now, to be honest, because our walking animation only, I think, has about a 1.6 speed, we should probably set that down to 1.6. Now, not that this is going to make any difference. If it was 5.6, we've only got walking animations in our blend tree, so the nav agent is not going to be going at 5.6. It can only go as fast as the walking will allow it, but it just seems right that we should set that to roughly what the walking speed should be. So we've had this problem with desired velocity. There's an easy fix. What we want to know is not the magnitude of the desired velocity vector, which is always going to be pretty big. We want to know how much of that velocity vector is projected onto our own forward vector, as this really tells us how much we should be walking forward. Now, why this helps is because as soon as we get to that waypoint, the desired velocity vector is going to point 180 degrees in the other direction, which means to us we're then going to have a negative speed value. So that's going to fall to 0 very quickly and do exactly what we want it to do. So we have to make a quick fix to the code, but it's very simple. As we already have the nav agent's desired velocity in our own local coordinate space, this is local desired velocity, all we need to do is delete magnitude and use the z component to set our speed. This is how fast we are walking forward from our own point of view, down our own forward vector. So you can imagine that if you come out of a steep turning, that's going to be quite a small amount. So that could cause us to actually do a turn on the spot there as well. So let's see what that looks like. That should have fixed everything, I believe. Okay, so far so good. Although that's a silly thing to say because the problem wasn't here. It was okay here last time. Here she comes. Don't let me down, Jill. Do not let me down. Hey, look at that. And now we have a pretty convincing, although slightly calm, patrolling zombie. Come on, Jill. Do your thing. Do your thing. Don't let us down. Okay, so this looks pretty cool now, especially if you see it in the game view. Root motion's great, right? Now, we are making it very easy for ourselves at the moment because our zombie is just walking. And, because the zombie is going quite slow, it means that we're never really going to have much problem sort of cornering. But in a moment, I'm going to show you where the problem really arises. And this is why I can't just use root motion like this in Dead Earth without a few little other tips and tricks that we throw in, and a few little cheats and hacks as well, so that the zombie can always kind of keep up with us and erratically chase the player around the level and still get all the cornering that it needs. Yeah, so there you go. That's absolutely fine. So the previous example was a good demonstration to show the concepts of using root motion to control our character, but it wasn't really a very realistic one, not unless we want all of our zombies to walk. Our walk animation was very slow, our turning animations pretty steep, so even if the animator gave the NavMesh agent a completely different velocity and direction to that which it asked for, it had plenty of time to make course corrections such that it could avoid geometry. The same cannot be said though for a real game situation when we're going to have our zombies sprinting after the player and trying to make very tight turning angles to keep up with the player's movement. The sad fact is we're just not going to have the variety of running and turning animations that we need to allow the zombie to achieve all of the turning arcs that it needs to keep up with the player and present itself as a threat. For example, imagine a zombie runs up to the player and then starts to play an attack animation. If the player then just quickly moves to the left or right of the zombie's going to have to sort of drop back out of its current animation into a turn on the spot animation wait until it's faced the player again, and then attack again. And that's just going to be so slow that the zombie would never be able to hit the player. Now, to show you what I mean about the inaccuracies that can creep in once you start using animations that don't have the turn varieties you need, I'm going to select my locomotion blend tree. I'm going to drill down into it, and I'm going to change the motion fields of the blend tree. So I'm going to go to the Unity Technologies folder in our animations folder, and I'm going to replace the walk with a run, and that is the run forward, neutral face forward, like so. And we don't have really tight turning angles for our run animation. So I'm going to use the tightest turning angle I've got, which is this one here, called run forward, turn right, medium. So I'm going to drag the left. Oops, let me select my blend tree again. So I'm going to select the run left medium and put that to replace the walk left short. And I'm going to drag over the run right medium and put that so it replaces the walk right short, like so. And I think to demonstrate this problem even better for the time being, what I'm going to do is I'm going to select the transitions from locomotion back to idle, and I'm going to click the mute tick boxes in the transition inspector. What this basically does is, you can see they're all highlighted red now in the animator. I've essentially disabled these transitions. So once we start, we're going to transition from idle into locomotion, and then we're going to be solely relying on the root motion that's contained inside this blend tree. Okay, so what I'm going to do before I press play is I'm going to also select the main camera, and I'm just going to speed up the camera's following of the character. Just because we're playing running animations now, so we're probably going to see the zombie run off of the screen. So if I press play now, what you're going to see is the zombie is still going to follow its path, but what you're going to see is it's going to bump into doors and walls, but it just doesn't have the turning angle it needs. You see it's even overshooting the mark on these shallow corners. It's taken them using quite wide arcs. Wow, actually managed to get around there. It's overshot the mark a bit there. It's probably going to not get out of this room gracefully. There you go, it's bumped into the wall, then bumped into a door frame. So we're seeing that while the NavMesh agent does its best to do course corrections when it's thrown a curveball by the animator's root motion, we are still going to see these situations. Now, of course, this is made better again if we have the turn on spot animations once again enabled, like so. But we can't rely on a turn on spot animation being played all the time. You can see what this is doing now, because we're overshooting the mark. We're actually getting a lot of these turn on the spot animations for turns that we never had them before. You can see it's just very unelegant, it's very inaccurate, we're bumping into bits of geometry, we're overshooting the mark because we're running, and that's forcing us into many more turn on the spots than we actually need. And like I said, if you imagine that the zombie was attacking the player, it would be very easy for the player just to sort of jump behind the zombie, and the zombie would then have to come out of its attack animation and do one of these really sort of slow turn on the spot animations. And it's going to be so easy for the player to never be hit by the zombie if every time it dives out of the way, the zombie has to go through this laborious turn on the spot sequence. So we need a way where we can have our zombie running around the level, but we can have it much more accurate at navigating the level. And we're going to do that by sacrificing a little bit of the root motion, in particular the root rotation. And I'm going to show you how we're going to do that now. So with this third solution, we are going to throw away root rotation altogether. We're not even going to let the NavMesh agent control the root rotation. We're simply going to override the rotation of the game object ourselves in the update function to make sure that the character is always facing exactly in the direction of the NavMesh agent's desired velocity. Now, this will obviously see us in extreme scenarios visibly sliding on the spot, such as when we do a 180-degree turn. However, I think what you'll notice from this technique is that for the most part, when running around the level, you're not really particularly aware that we are rotating the character on the spot. It still looks pretty convincing, but the character becomes extremely agile and accurate. And then what we'll show after that is a technique where we can mix both root motion for certain states and use the technique I'm going to show you now for other states. So let me go back to the source code, and in particular scroll down to our onAnimatorMove function. And for now, I'm just going to comment out the line that applies the animator's root rotation to our game object. Now you remember up in the start function that we've also disabled update rotation for the nav agent, so currently nothing is updating the rotation of our game object. We're going to do that now, right here. So I need to create a new rotation quaternion that I can assign to the rotation member of my transform that describes the rotation of our game object such that it is looking in the direction of the NavMesh agent's desired velocity vector. Fortunately, Unity has the quaternion class, and in particular the quaternion.lookRotation function specifically for this task. We just pass in the look and up vectors that we wish to have a quaternion created for, and the returned quaternion can then be assigned to the rotation member of our transform. So I'm going to create a new local quaternion. I will call this look rotation, and I'm going to set this equal to quaternion. Now this function that I'm using is a static member of the quaternion class, okay, so we use the quaternion class, not an instance of a quaternion, and the function I'm going to use is look rotation. And for the first parameter I need to send in the forward vector that describes the direction that we wish this quaternion to be facing then. So I want this to be the NavMesh agent's desired velocity vector, like so. Now I could just leave it at that, but you also have another variety of the function that allows me to specify the up vector, and I'm going to do that just so that I'm very clear when this rotation is being created that I consider the up to be the up of the world. So that's just a vector that is 0, 1, 0, but there's an even better way to get it by just using the vector3's static up property, like so. So that's going to create a quaternion that we can now assign to our transform. But because we've discussed in the past the desired velocity can be a little bit spiky, what I'm going to do is I'm going to smoothly move from the transform's current rotation towards this rotation. So I'm essentially doing the same thing that I did when we set our floats and we smoothed our angle, but I'm doing it with quaternions. So I'm going to say transform.rotation equals, and I'm going to use the quaternion slurp function for this, which does a spherical linear interpolation over time from our source quaternion to our target quaternion. So the source quaternion is the rotation that our transform currently has, and obviously the target rotation is the look rotation quaternion we created up above, and I think I'll just use something like 5 times time.delta time. We don't want this to be too slow, or once again we're going to have the NavMesh agent battling with sort of overshooting the mark. So if this is the rotation we want our game object to have, we want to get there pretty quickly but with a bit of smoothing. So if I run that now, we're going to forcefully always set the transform to look in the direction of the desired velocity, and in the onAnimator move function you can see we're throwing away the root rotation. Now the only thing I'm going to have to do here is I'm just going to have to put a little test around this, because the quaternion look rotation function is not going to be happy with me, and it's going to produce an error in the console window if desired velocity is ever a 0 vector, which it can be. You know, if the character has come to a stop and it has no target, then you know, we might have a 0, 0, 0 vector. So I'm just going to put around that code a conditional that says if navagent.desired velocity vector dot, and I'm going to use squared magnitude here, okay, just because it's quicker than doing a full magnitude, because it doesn't do the square root. And I'm just going to say as long as it has some length. So for that I'm going to use a very small value, something like 0.0001. I'm going to use the mathf.epsilon property for this, which is essentially the same thing. Okay, it's just a very small floating point value which is used for tolerance situations like this. Okay, so that should stop me getting that error. All I'm saying is only use the desired velocity to update the rotation of our game object if we have a valid desired velocity vector that has some length to it. Now what you should see now is an error. What am I doing? Sorry guys, I was treating the slurp function as if it was the smooth function of set float. It's just 3 parameters. I meant to say 5 times time.delta time, not 5 comma time.delta time as the third parameter, which controls the speed at which we interpolate from our source to target rotations. So now that should be error free. And when I press run now, you're going to see that our running sort of character is now very dependable. It's not overshooting the mark, it's getting in and out. You see there it spins completely on the spot because we're always forcing the rotation of our game object to force down the desired velocity vector. Therefore, there's never a situation where the angle between our current forward vector and the desired velocity vector is ever anywhere near 80 degrees. So we're never going to see those turn on spot animations get triggered. But what you can see now is that for the most part, except for where we spin on the spot 180 degrees, when it's cornering, even tight corners like 90 degrees, it looks fine. We're not really noticing the foot sliding. So what I'm going to do in Dead Earth is I'm going to use this for most of my sort of patrolling behaviors, and I'm only going to drop down into sort of root motion when we want to do turn on the spots and things like that. And that's only going to happen when we decide that the angle we wish to turn onto is so great that we feel that spinning it on the spot would be noticeable. Such as here, look, we get here, it spins on the spot, it's very noticeable. But even when we're cornering here at 90 degrees, looks fine. And I think in the heat of the action, when these things are chasing you, you're not really going to be particularly aware of that. So what we have is, our position is being controlled by root motion and is driving the nav mesh agent, but our rotation is being overridden by ourselves, and we're always facing it down the desired velocity vector. So what I'm going to do now is I'm going to create a kind of a mixed mode version of this, which shows us how we can use this for normal locomotion, but also have our turn on the spots activated. But now we can't use the turn on the spots when we're using this quaternion look rotation method, because even if we slowed the rotation down, our turn on the spot looks ridiculous if it's not using root motion. So what I'm going to implement now is a mixed mode version of this script. Actually, I'm just going to add a mixed mode boolean to it that's going to allow us to specify that when we're in the locomotion state, we're going to use this system that we're using now. But as soon as we detect that we've got a wide turn angle, we're going to drop down into idle and on one of the turn on spot animations, and only when these are active are we going to switch back to using the root motion. So we're going to get the best of both worlds, right? We get really good responsiveness when we're running around the level chasing the player, always facing the player at all times, until we realize that we have a really tight angle that we need to turn through, which may be noticeable, in which case we're going to drop down into the idle, root motion is going to kick in, stop our character, and then we're going to be able to rotate left and right using root motion, and then eventually start running again. And when we get back into our locomotion state, root motion, or at least root rotation, will be disabled again. So how are we going to do that? Well, the first thing I'm going to do is go back to my code, and I'm going to add a new public variable to this class, and I'm going to call it mixed mode. It's going to be of type boolean, so that we can turn this behavior on and off. And I can set this to true by default, which means we do want to see this combination of the two techniques. Okay, so let's scroll down to our update function now and make some changes. So here's the code we just added, which, assuming we have a desired velocity vector, is unconditionally executed. What I want to do now is I want to change the conditions under which this is executed. So one condition is if we are not in mixed mode. If we turn mixed mode off, then we just want the script to work like it did just now when I press play. So I'm going to say if we're not in mixed mode, that's our first clause, or if we are in mixed mode, and if the angle that we've calculated above here, not the smoothed angle, I want to use the actual angle between our forward vector and our desired velocity vector. If that angle is larger than 80 degrees, then we wish to also step into this code. But remember, the angle can be both negative and positive, so we want to take the absolute value of it. So I'm going to say mathf.abs angle, and this is the more interesting bit. If the current state that is playing in the animator on our base layer is the locomotion state. How do we know that? Well, the animator has a really cool function called get current animator state info. This returns an animator state info structure which has several variables, and in production code you would actually make sure that you created those hashes of the parameters and the state names, and you would use either the short name hash, which would be, for example in this case, locomotion, or the full path hash, which would be base space layer dot locomotion. But we're going to just use the isName function, okay, which is going to kind of force the function to convert the string we pass in to the hash behind the scenes and then do the comparison. Now the isName function takes the sort of full path of the state, so that's in the format of layer name dot state name. So what I'm going to say then is animator.getCurrent animator state info. I pass in as its only parameter the layer index, which is 0, our base layer. And I say then is name, and then I need to pass in the full path of the state, which remember is a string in the format layer.name. So that is a base layer, I think it's base layer with a space, dot locomotion. If the angle is smaller than 80 degrees, which I haven't even put in there yet, so let me put that value in there. So if the angle is smaller than 80 degrees and the current state playing on the base layer is our locomotion state. Okay, we don't want to trigger this if we're currently in the middle of an idle state or one of our turn on spot states. I need to get rid of that at the end and then wrap that code in the curly braces. Okay, I think that's that. So now I'm going to go down to the onAnimatorMove function, do something a little bit similar. I'm going to say we only want to apply root rotation if we are in mixed mode, and exactly the same thing is true. We are in the locomotion state. So I'm just going to copy that over from the update function like so. Then we're going to apply the rotation that's given to us from the animation clip that's currently playing, all right? Okay, and of course, actually, I've made a mistake there. It should be if we are in mixed mode and we are not in the locomotion state. Remember, it's in any other state other than the locomotion state that we want to apply root rotation. Then that should work. So let's try that. So when it starts off, we should see us in the turn on spot animation. Yep, root rotation. Then we're running, all is cool. We're not using root rotation. We get in there. Yep, the angle's dropped. Root rotation. Dun, dun, dun. So this is a pretty nice combo. Now, obviously, the way I've implemented this at the moment has been very kind of hodgepodge, right? I'm kind of throwing all of these things in and hard coding a few things. But what I'm going to do in the actual code, which we're going to start creating very, very soon, when we design our larger AI system, we're going to actually apply scripts to our states, because there are these things in Unity 5 called animation state behaviors, which allow each of these states to have a script that can actually talk to our mono behaviors. So in that particular situation, the state itself, when it's activated, is going to communicate with our behavior and say, hey, I want root rotation and root position for this, or I don't want root rotation, whatever. So the animation state machine itself is going to be also dictating this and telling our code whether root rotation should be applied. So that's all very cool. I suppose I should just check that it works as it did before. If I untick that mixed mode boolean, we should not get the turn on spots now. It should be purely locomotion state driven. Yeah, there you go. So we have covered a lot of stuff in this lesson. There's a lot of things for you to experiment with. So the script that I've created in this lesson, the nav agent root motion script, and also the other one, which was called nav agent no root motion, they're also going to be available in the zip file that accompanies this lesson, just in case you can't be bothered to type it in. But you know my stance on that. You should be typing this code in along with me, because you know, if when you make mistakes, grammatically speaking, if you're new to C#, it's going to help really cement the syntax of the language in your mind. So I think that has been quite enough for today, don't you? It's been about my least favorite subject, animation and navigation combined. And as a result, I'm knackered. So there's obviously some stuff that we haven't discovered, such as bringing in off-mesh links. We haven't discussed using state machine behaviors, but because I don't want to keep putting off the development of the actual game and the actual code, I'm just showing you kind of what you need to know before we go into it, and the rest of that stuff I'm going to cover in the context of actually creating the real game systems, okay? So this has been Gary Simmons once again for the Game Institute and the Dead Earth game development series. I will see you in the next video, folks. Bye bye now.